Hello there, Mr. Sutton here with the AB Calculus 611 classwork solutions on accumulation and rate in, rate out free response practice. For this problem, the setup is that we have a storm washing away sand from a beach, causing the edge of the water to get closer to a road, and the rate at which the distance between the road and the edge of the water is changing is modeled by this f of t function. They're telling us the edge of the water is 35 meters from the road originally, the storm lasts 5 hours, and the derivative of f of t, f prime of t, is given here as well. All right, so first part, we want the distance between the road and the edge of the water at the end of the storm. So for this, we need to take into account the 35 meters distance that the water and the road had between them at the beginning. And then we have to add in the integral of, let's see, this rate of change right here. This is the total. If you integrate this f of t, this is going to be the total change in the distance between the road and the edge of the water. So we're going to do integral from 0 to 5 of f of t dt. And let's use the calculator for that. Now, to set myself up for success on this, I'm going to put this function inside my y equals and y1 because I'm probably going to end up using it more than once. And it's easier to move around anyway when it's just y1 instead of all that. All right, so I've got 35 plus my integral, so math 9, from 0 to 5 of alpha trace y1, that's my f of t function, and I'll make this a dx. And that is going to be a distance of how much? 26.495, and that's going to be in meters. For part B, they're giving us the value of f prime of 4 as 1.007, which we probably could verify if we wanted on our calculators. But what they want us to do is interpret what this means in terms of the distance between the road and edge of the water. So there's three elements we have to have in here. We need the time element. So at time 4 hours, so 4 hours since the storm began, and now we need the what. What does this actually mean? And then we're also going to need units. So to say that this is 1.007, what we are saying is that the rate at which the road water distance is changing, which is given by f of t, this rate itself is increasing at a rate of 1.007. And what are the units on this? Well, f was in units of meters per hour. F prime, this is the change in this with over each hour. So this is actually going to be meters per hour squared, or meters per hour per hour. For part C, we want to know at what time during our 5 hours of storm was the distance between the road and edge of water decreasing most rapidly. Justify your answer. So the function in charge of decreasing our distance is this f of t function. So decreasing most rapidly means that we want this thing to be as negative as possible, which is to say we want to find the absolute min of f of t on 0 to 5. Okay, well, to figure that out, I'm going to need to find critical values of f prime of t. Now, there's a critical value at 0 because that makes f prime of t undefined, but 0 is already one of our endpoints because we're going from 0 to 5, so we're going to test it anyway. So let's just focus on critical values that make f prime of t come out to 0. To figure that out, I'm going to go ahead and graph this on my calculator. Before I can graph it out, I have to actually enter f prime in my y equals. I'll put that under y2. And I don't want to graph out f of t itself, so I'm going to exclude this. I'm going to unselect it. Now, to graph this out, I need a window. I'm going to choose the window from 0 to 5, because that's when the storm was going on. And let me zoom fit this now. Zoom 0. So here is f prime of t. So we've got one critical value before we get to 1, and there's another critical value over there. Now, if we're looking for the absolute min, we only need to look at local mins for critical values. This critical value over here, where f prime is changing positive to negative, that's a local max, and there's no way a local max could ever be the absolute minimum of a function. So we're just going to focus on this critical value over here, and then we'll word things so that we only need to plug this value in, not this other value. So let me do second trace, 0, and my spider's almost there. A little bit to the left, we'll press enter. A little bit to the right, enter, enter again. and we have a critical value of 2.8404, which I'm going to quit out of here and immediately store that as a variable, as a letter rather. I'll go with alpha A. That's just my favorite one to use. And now what I'm going to write here, so here is the graph that we just saw. I'm going to say that this equals 0, and that f prime changes from negative to positive at t equals a equals 2.8404 only. So I've done a few things in this statement. By saying negative to positive, I'm establishing that I've got a local min, which is a type of critical value. I'm also, since I said only, I'm saying that, well, I'm only going to consider local mins. I don't have to worry about local maxes. So this gets me off the hook for plugging in this other point. And then finally, notice that I called this A. So now instead of writing this bulky number, I'm just going to write A. All right, now it's time for the candidates test. So we have to test the endpoints of 0 and 5 and also this critical value of A. Let me go to the f function now to test out 0. So I stored f under y1. Let me do alpha trace y1, and I'm going to plug in 0 now just to see what I get. And that's going to be -2. You actually could have probably done that without a calculator, but hey, if you're allowed to use a calculator, then I would use it. Next, I'm going to plug in A to that same function. So I'm just going to go and yank my input from before, and I'm going to replace 0 with alpha A. So there we go. And that comes out to about -2.2696. So that's 2.70 if we round it off. And finally, I need to test out 5. So back to the calculator we go, yanking that former input, putting 5 there instead of A. We get -0.480. So looking at all of these, the most negative value, the absolute min, is going to be at time A. For this last part of the problem, which is kind of wordy, after the storm, a machine pumped sand back onto the beach, so the distance between the road and the edge of water was growing at a rate of g of p meters per day, and p is the number of days since the pumping began. So given this, we want to write an equation with an integral expression whose solution gives us the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. All right, so one way of thinking about this is we can take the amount of distance between the road and the water that was left after the storm, which we found in part A. We found that that number was about 26.495, and we can add to that an integral with this g function in it. So g is the rate at which the distance is growing. So if I want to find out the total rate that I need to integrate that from, we'll say, 0 to t, because I can't have a p in there. So I'll put a t in my upper limit of integration, and inside I'll have g of p dp. All right, so this is the total sand that gets pumped in from 0 to day t. Great. Now, what does all this equal? Well, I want to pump in just enough sand so that I restore this 26.495 to 35. So hopefully if I have what I had after the storm and I add this sand pumping integral in here, I end up with my original amount. Now, another way of writing this, you could have written it as follows. So I could take the amount of distance after the storm, or rather I should say the change in the distance between the road and the water after the storm. That's what this integral from 0 to 5 of f of t is giving us. If I take that change and negate it, because it's originally going to be negative because you're losing that distance, if I make this positive now, then that should equal the amount of sand that I have to pump back in over t days. For this problem with a unique situation here, when a certain grocery store opens, it has 50 pounds of bananas on display table. And then customers remove those from the display table at a rate modeled by this f of t function. So this is the rate out of bananas. And this is measured in pounds per hour since the store opened. So after the store has been open for 3 hours, the employees start adding bananas back to the display table, modeled at a rate captured by this g of t function. So we have rate in for g, rate out for f. And same thing, measured in pounds per hour. All right, we want to know how many pounds of bananas are removed from the display table during the first 2 hours the store is open. So we're asking for the total accumulated out over the first 2 hours. To help with this, I'm going to put both of these functions in my calculator. So here I am in my y equals. I've entered f of t, the rate out, as my y1, and y2 is going to be g of t, my rate in. Okay, so I wanted to figure out during the first 2 hours how many bananas got removed. So that's going to be the integral from 0 to 2 of the f function up here, so f of t dt. For part B of this problem, they want us to find f prime of 7 and then explain what it actually means in the context of the problem. So let's do the mathematical part. To do f prime of 7, I'm going to do, just on my calculator, math 8, derivative, I have dx down there, and f again, that is in my y1, so I'm going to take the derivative of my y1 function in my calculator, and I'm evaluating that at x equals 7. Giving me the number negative 8.1195 and some change. So we'll round this off to 120. All right, so what does this actually mean? Well, f of t, that is the banana removing function here. This is the rate of banana removal in pounds per hour, pounds of bananas per hour. The derivative of that is going to be the rate at which the rate of banana removal is changing. So this is the rate at which the rate of banana removal is changing, and the units on this, since we're starting off in pounds per hour and we want the rate of that, this is going to be pounds per hour. So pounds of bananas per hour squared. And then the time element also needs to be included here. So this is the rate at times 7, and that's 7 hours. For this part of the problem, we want to know if the number of pounds of bananas on our table is increasing or decreasing at time 5. All right, so it would be very helpful if I had a function to describe just the overall rate of change in the amount of bananas. Now, I don't really need this for the first 3 hours, because they said for the first 3 hours, customers are just taking bananas and nobody's putting anything back. But after the store's been open for 3 hours, then we start putting bananas back. So what I'm about to do here, I'm going to define a b of t function to talk about the overall rate of change of bananas, but I'm only going to need it on the interval from 3 to 12. From the interval from 0 to 3, this f of t function is going to take care of the rate of change all by itself because nobody's putting anything back. But from 3 to 12, we need this b of t that accounts for people putting things back. So b of t, I'm going to define that as the rate in minus the rate out. G of t minus f of t. And now that I've defined it that way, I'm going to put this in my calculator and figure out b of, let's see here, they wanted time 5, so b of 5. So on my calculator, I'm going to define y3 as y2 minus y1. So this is essentially my b of t function here. This is g of t minus f of t. And then let me just quit out of there. I wanted to find b of 5. So alpha trace y3, open a parentheses with a 5 inside. Comes out to negative 2.263. So what does that mean? Well, that's a negative number, and this was the rate of change of overall bananas. So since this is negative, that means that the number of pounds of bananas is decreasing at time 5. For this last part of the problem, they're asking how many pounds of bananas are on the display table at time 8. All right, so there's a few things to take into account. First off, we can't forget about the 50 pounds of bananas that we started with, right? Don't want to forget about those. But then, for the first 3 hours, people were taking those away. So we're going to have to subtract the integral from 0 to 3 of f of t dt. This takes care of all the bananas that got removed by people over the first 3 hours. But now, after the first 3 hours, when the employees start adding things, we have a different function we need to integrate. Now we're going to add the total change in bananas from time 3 to 8. And total change in bananas, the rate of change of bananas, that's b of t that I defined on the last problem part. So I'm going to add the integral from 3 to 8 of b of t dt. And now I'm going to plug all of this in my calculator. So I've got 50. I'm subtracting the integral, so math 9, from 0 to 3. And my f function, I stored that in y1, so I'm going to put alpha trace y1 in here, dx. And then to that, I'm going to add an integral, so another math 9, from 3 to 8 of, well, this time I need the b of t function that I stored in y3, so alpha trace and then y3 out of that menu with a dx at the end, and press enter and hope for the best. So that's 23.347, and that is pounds of bananas. For this problem, we have a scientist measuring the depth of Doe River at Picnic Point. River's 24 feet wide at this location, and measurements are taken in a straight line perpendicular to the edge of the river. The data are shown in the table above. Did I just say data? Yep, I did. Anyway, let me give you a picture of what's going on here. This is a tough one to visualize. So I just kind of cut and pasted something off of the Google to help us out here. So here's what's going on. We have this scientist, and he's going across a river and basically measuring the depth at various points across the river. So, for example, if you're 0, let's say that our scientist starts on the left, just to make it easier to visualize. So let's say you have a distance of 0 from the river's edge. You're right here, and you have a depth of 0. And then as you move over, maybe you're 8 feet from the river's edge, like right over here, and now you have a depth of 7, and 14 feet you have a depth of 8, 22 feet you have a depth of 2, and so on and so forth. So that's what they're really representing in this table. This is kind of interesting because we have an input function of distance, of feet, and the output is also feet, but it's a different kind of feet. The input is basically distance from the edge. The output is depth down. And to make things even weirder on this one, the velocity of the water at Picnic Point in feet per minute is modeled by this v function, which has an input of time. So based on all this weirdness, let's just go through these one step at a time. Part A, they want us to use a trapezoidal sum with 4 subintervals, using the data in the table, to approximate the area of a cross-section of the river in square feet. All right, so we have all these depth measurements, and essentially we want to figure out the approximate area here by using a trapezoidal sum. So we're going to have a bunch of trapezoids, and we're going to be using the depth of the water as the basis of the trapezoids, and the height are going to be all these horizontal kind of increments here. So our first trapezoid, we're going to have a depth of 0 plus 7, so those are the bases. Divide that by 2 and multiply by a height of 8. And again, with these trapezoids, the height is kind of on its side here. Next, we have a trapezoid with 7 plus 8 over 2 times a height of 6 to get from 8 to 14. Then we have 8 plus 2 over 2 times the height of 8. And then 2 plus 0 over 2 times a height of 2. Now, if you just put units on the end of this, you're actually done. The units, since we're talking about area here, and feet is the one-dimensional unit, this would be feet squared. But you could, of course, plug this in the calculator. And if you do what I did and plug all of this in your calculator using Francie fraction for these crazy fractions here, all of this comes out to 115. And again, either way, that's going to be in feet squared. For this next part of the problem, and I'll keep my little diagram around here, the volumetric flow at a location in the river is the product of the cross-sectional area, so this area here, and the velocity of the water at that location. So we have some water coming this way. If you multiply the velocity at a certain time at this spot with the area, that gives you the volumetric flow. Okay, so we want to use our approximation from part A to estimate the average value of the volumetric flow at Picnic Point from time 0 to time 120. So we have an average value, first of all. That means we have to do 1 over the interval length. So that's 1 over 120 minus 0 times the integral from A to B. So integral from 0 to 120. And now we're going to stop for a second, figure out what we're actually taking the average of. So they actually spelled it out for us. They said the product of the cross-sectional area and the velocity. Well, the cross-sectional area that we estimated in part A was 115 square feet. And the velocity is just given by this v function up here. So we'll do 115 v of t dt, and now we'll need to use the calculator to actually get this number. To make my life a little bit easier on this problem, I'm going to put this velocity function in as y1, and there's a little bit more if we scroll to the left here, so we had 16 plus all that stuff. And now, moving my calculator so I can see all of this, armed with this y1 v of t, I'm going to quit out of there, and let me do fancy fraction here, 1 over 120 times math 9. So I want my integral from 0 to 120 of, we had 115 from part A, and now I stored my velocity in y1, so let me do alpha trace y1, and then dx. All of this comes out to what? This is 1,807 this will be 170 if you take it to 3 decimals. And what are we multiplying together here? So this is going to be, well, they told us here, flow is going to be cubic feet per minute. So that was nice of them, feet cubed per minute. On part C of this problem, our scientist proposes a function given by f of x to model the depth of the water. So basically, doing what this table does, but with a function instead of a table. We want to again find the area of the cross-section using this model. Okay, well, if I'm finding the area of a cross-section, you could think of this model as kind of like giving me a line on a graph. And if I want the area of the cross-section, I'm just finding the area under that line, or over that line in this case, since it's depth instead of height. Well, if I want to find the area under a line, I'm essentially asking for the integral of this function. So I'm just going to take the integral of f of x over the course of this river cross-section here, so from 0 to 24 of f of x. And now let me do this on the calculator. So on my calculator, I took that 8 sine of pi x over 24 function that they gave us here, and I just put that in my y2, again, just to make it easier to work with. So let me quit out now. And now let me do math 9, 0 to 24 of alpha trace y2 now, because that's where I stored my f function, and then dx. And this comes out to 122.231, and that again is going to be square feet because this is area. And you might be wondering why I'm storing this on my paper as the value A. Well, I am going to need it a little bit later. I just kind of looked ahead to part D. But when you see an A in part D of this problem, this is the A we're talking about, is this cross-sectional area that we got the exact value of using this scientific function. For this last part of the problem, recall that volumetric flow is the product of cross-sectional area and velocity at a location. Well, how could we forget? To prevent flooding, water must be diverted if the average value of the flow exceeds 2,100 cubic feet for a 20-minute period. So using our answer from part C, we want to find just the average flow on the time interval 40 to 60 minutes and see if this value indicates that water must be diverted. All right, so they said using our answer from part C, so I'm going back to my calculator right away, and hey, I'm going to have to use this again. So I'm going to yank this value, and I'm actually going to store this as, I'm going to say alpha A. So now I can just plug in A and get this back whenever I want. Okay, so I need an average value over the interval from 40 to 60. I'll start with 1 over 60 minus 40 to give me the interval length. And now I know I need an integral from 40 to 60. An integral of what? Well, again, and it's nice they reminded us, we have the product of area and velocity. The area I just figured out in part C, and I stored that as A, both on paper and on my calculator. Velocity is still what it is. It's just v of t again. So we're going to run these numbers on our calculator now. So here's what I've entered in my calculator. I have my interval length, 1 over the interval length, integral from 40 to 60, and then constant A that I stored this in just a bit ago. And then y1, again, that's where I stored my velocity function. dx for the end of this, and now pressing enter. This all comes out to 2,181.913. And that, again, is going to be in cubic feet per minute. That's what they said before. Now, they said that we have to divert water if our volumetric flow is greater than 2,100. This is definitely greater than 2,100. Therefore, we are going to have to divert some water.